We throw the word voltage around all the time, but have you ever stopped to think about what it actually is? It's one of those concepts that feels, well, a little invisible, right? So today, we're going to change that. We're going to make it totally visible. We're going to demystify electrostatic potential and even capacitance by building this really simple but super powerful analogy of an electrical mountain.
All right, let's just jump right in. The big question, what is voltage, really? Now, to get a handle on this, to get a real intuitive feel for it, we're not going to start with a bunch of crazy equations. No, we're going to start with something way more familiar to all of us.
Okay, so our story here starts with a really fundamental idea. It's all about storing energy by pushing back against some kind of invisible force. So just picture this. You're lifting a heavy rock off the ground. That effort, that strain you feel, that's you doing work against gravity. But here's the cool part. That work you put in isn't just gone. It's literally stored inside that rock as potential energy. And the higher you lift it, the more energy you pack into it, just waiting to be released. It's a super simple idea, something we've all physically felt. And here's where it all clicks. It turns out that the electrostatic force, the Coulomb force that pushes and pulls on charges, it behaves almost exactly like gravity does with mass. They're both what we call conservative forces, which is just a fancy way of saying that any work you do against them gets stored as potential energy. And, get this, they both follow the same inverse square law. So this whole electrical mountain idea, it's not just some cute metaphor. It's actually grounded in some really solid physics.
All right, so if these electrical forces are acting just like gravity, then it kind of makes sense that they'd create their own sort of landscape, right? With hills, peaks, and valleys. So let's do it. Let's start drawing a map of this electrical terrain.
Okay, imagine a single positive charge just hanging out in space. We know it's going to repel any other positive charges that come near it, right? So in our landscape analogy, what does that look like? Well, it creates this perfect symmetrical hill. If you want to push another positive charge closer to it, it's just like trying to shove a boulder up the side of that hill. It's going to take some serious work.
But here's where it gets really fun. What happens when you have more than one charge? Let's say you have an electric dipole that's a positive charge and a negative charge near each other. Suddenly, your landscape gets way more complex. You don't just have a simple hill anymore. Now you've got a towering peak right next to a deep, plunging valley. You've basically created a whole electrical mountain range. So, if you've ever looked at a topographical map, you've seen those contour lines, right? The lines that connect all the points that are at the exact same altitude? Well, our electrical landscape has the exact same thing, and we call them equipotential surfaces. And here's the key takeaway. Since the altitude is the same all along one of these lines, it takes absolutely zero work to move a charge along it. It's literally like taking a nice, easy stroll along a flat path that circles a mountain. Okay, so if the equipotential lines are the easy, flat paths, then what about the electric field lines? What do they show us? Well, they show us the force. They point in the direction the charge would get pushed or pulled. And in our mountain analogy, that means they always point along the most direct path up or down the slope, the steepest possible route, which is why they're always perpendicular to those flat contour lines. Makes sense, right? So, we've got our landscape, we've got our map, we've got the contour lines, but what exactly is the height? What does the altitude on this electrical map really mean?
Okay, let's get the official definition on the table. Electrostatic potential, which, you guessed it, is what we call voltage, is basically the total amount of work you'd have to do to drag one unit of charge from way far away, like from infinity, all the way to a specific spot on our landscape. So it's really just a measure of how much energy is stored at that one single point.
And there it is. That's the whole secret. Voltage is nothing more than the electrical altitude at any given spot in our landscape. That's it. So a point with high voltage, that's like standing on a tall mountain peak, just brimming with potential energy. And a low voltage point, you're down in a valley.
Now, this little quote here is absolutely crucial. Think about it. A rock sitting on a perfectly flat tabletop high in the mountains isn't going to roll anywhere, is it? It needs a slope. And it's the same for charges. A charge won't move unless there's a difference in electrical altitude, a slope. It's this potential difference, the voltage between two different points, that actually drives the electric current. It makes all the cool stuff happen.
All right, so our landscape has mountains and valleys. Pretty cool. But now we're going to add a really strange new feature, giant, perfectly flat plateaus. And these are our conductors. So conductors have these really specific, kind of weird rules they always follow. First, when things settle down, the electric field inside a conductor is always zero, always. Second, any extra charge you put on it, it zips right to the outer surface.
So, because that field inside is zero, it takes zero work to move a charge around in there. Now think about that. If it takes you no effort to move from point A to point B, what does that tell you about your altitude? It means your altitude isn't changing. The potential, or electrical altitude, have to be the exact same everywhere inside and on the surface. The whole conductor becomes one big equipotential region. And in our landscape, that's a perfectly flat plateau. You can wander all over it, and your altitude, your voltage, never changes one bit.
Okay, we've got a pretty amazing landscape now. We've got peaks, valleys, and these awesome flat plateaus. So the next logical question is, how can we use these features to build something, like a device that's specifically designed to store up all this energy?
Well, say hello to the capacitor. A capacitor, when you boil it right down, is super simple. You just take two conductors, two of our flat plateaus, and you put them really close to each other. But, and this is important, you separate them with an insulator, so the charge can't just jump from one to the other.
The best way to think about this is like building a water reservoir on a mountainside. The two plates are like the walls of your reservoir. And capacitance, that's just a measure of how big your reservoir is. So a capacitor with a large capacitance is like a huge reservoir. It can hold a ton of charge, or water, for a given electrical height, a given voltage, which is like the height of the dam. So, how do we actually fill this energy reservoir? Let's build one, step by step. First, you start with two of our flat conducting plates, our plateaus. Second, you hook up a battery. Now, the battery acts like a powerful pump, and it does the hard work of pulling charge off one plate and shoving it onto the other. Third, doing this creates that all-important potential difference, that V, between the plates, and that sets up a nice, uniform electric field in the gap. And boom, the work that the battery pump did is now perfectly stored as potential energy, right there in that electric field.
And here's a look at the most classic design of all, the parallel plate capacitor. It's just a really simple, super effective way to create that uniform electric field that's going to be our energy reservoir. But here's the really mind-bending part of all this. The energy? It isn't actually stored in the charges themselves or even on the metal plates. No, it's stored in the electric field that exists in the empty space between the plates. Which leaves us with a pretty deep and fascinating question to chew on. What does it actually mean for nothing, for empty space itself to hold energy, to be stretched and stressed and filled with potential? Kind of makes you think, doesn't it?